So once again, a very good morning to all of you. So in the today's class, we are going to discuss about the applications of steady flow energy equation pertaining to a few devices like boiler, turbine, and nozzle. So the motivation is it is essential to know the working principle and performance evaluation of boiler, turbine, and nozzle, which are very important devices in a thermal power plant. So the outcome of this lecture is, so you should be in a position to derive the steady flow energy equations for the boiler, turbine and nozzle, and similarly you should be in a position to solve some problems based upon the steady flow energy equation of the boiler, turbine as well as the nozzle. So these are the outcomes I'm expecting from this lecture. So now let us discuss the first important device, that is the boiler. So before deriving the steady flow energy equation of any engineering device, so it is very important to know first of all what is the function, what is the purpose of using this particular device. That is why we have to use the boiler. So the boiler is an important device in the thermal power plant to produce the steam from the water. So that is the whenever we are giving some heat energy to the water, so water is converted into the steam. So this steam may be wet steam or dry steam or the superheated steam. The various forms of the steams we are able to obtain it from the boiler. So now, after knowing the purpose of the boiler, then how can you derive the steady flow energy equation for a steam boiler? So now, what is the main input, that is which one is to be calculated whenever you are solving the steady flow energy equation of a boiler? That is, how much amount of the heat energy is supplied, how much amount of the heat energy is supplied to the water to convert into the steam. So our intention is here to calculate how much amount of the heat is supplied to the water. So that is our main intention. That is, our intention is to calculate delta Q. Delta Q. So here, so I've already told you that the steady flow energy equation is nothing but H1 plus C1 square by 2 plus ZZ1 plus delta Q is equivalent to H2 plus C2 square by 2 plus ZZ2 plus delta W. So here, which parameters can be neglected while we are deriving the steady flow energy equation? Now, whenever we are dealing with the steam boiler, we are assuming that there is no changes in the kinetic energy as well as in the potential energy. So since the changes in the potential energy and the kinetic energy are neglected, so C2 square by 2 and C1 square by 2 are equivalent to 0. And similarly, delta Z, that is the Z2 minus Z1 is also equivalent to 0. So boiler will not produce any amount of the work. So that's why the work also can be taken as 0. So whenever you are implementing all these assumptions in the steady flow energy equation, then automatically this will become H1 plus Q is equivalent to H2, or Q is equivalent to H2 minus H1. That is, our intention is to find out how much amount of the heat is transferred to the water. So the heat transfer to the water is equivalent to the increase in the enthalpy content of the steam. That is, the H2 minus H1 is nothing but increase in the enthalpy content. So Q is equivalent to H2 minus H1. So similarly, now let us concentrate on the next device, that is the steam turbine or the gas turbine. So I told you that for any engineering device, it is very essential to know what is the purpose of using that particular device. So now let us understand for what purpose you are using the steam turbine or gas turbine or hydraulic turbine. That is, the turbine is basically used to generate the mechanical work. That is a work producing device is the turbine. So from the turbine, we are expecting some work output. So this mechanical work is converted into the electrical power whenever the turbine is coupled to the generator by means of a shaft. So automatically the mechanical energy is converted into the electrical energy or the exit of the generator. But at the turbine exit, so strictly we are speaking, it is a mechanical work. So mechanical work is produced by the turbine. Now, what are the assumptions? That is, here our basic intention is to how much amount of the work is produced by the turbine. That is delta W value we have to find it. So that is very important one. So here also we are assuming that the changes in the potential energy is equivalent to 0, that is the Z1 and Z2 is equivalent to 0. So then automatically here H1 plus C1 square by 2 minus Q is equivalent to H2 plus C2 square by 2 plus W. So here why we are keeping minus Q here I have written Q is negative because heat is rejected from the system, because here the heat is rejected. Suppose if you take it is an adiabatic turbine, then automatically Q is equivalent to 0. So it is basically depends upon the assumptions which are given in the problem. Suppose you say that is insulated, the turbine is insulated or adiabatic, then automatically Q can be 0. And sometimes you may say that the changes in the kinetic energy may be neglected. Then C1 square by 2 and C2 square by 2 also can be neglected. So then we can write down the formula only in terms of W. So W is equal to only H1 minus H2 when kinetic energy is also equivalent to 0, and whenever it is insulated we can say that W is equivalent to H1 minus H2. That is, the decrease in the enthalpy content of the system is taking place, that is in the steam or gas turbine. So the next device is the steam nozzle. So what is the function of the steam nozzle? So steam nozzles are normally classified into the convergent nozzle, divergent nozzle, and the combination of the convergent and divergent nozzle. So here in the picture 4.40, it is representing the convergent divergent nozzle. So what is the function of the nozzle means it is used to increase the velocity of the steam by decreasing the pressure. So whenever I am saying that the velocity of the steam is increased by means of the steam nozzle, how it is possible? It is only by having decrease in the pressure of the steam. So what is our intention here in the steam nozzle steady flow energy equation is we have to find out how much gain in the velocity of the steam we are able to expect at the outlet of the steam nozzle. That is the V2 value we have to find out, V2 or C2, whatever it may be. So here we are taken as the C2, but sometimes it may be V2 also. So our intention is to find out the C2 determination or V2 determination. So here also the changes in the potential energy can be 0, and it is the adiabatic nozzle. So it is just, you can see it's the hatching area. Hatching area indicates it is adiabatic. So delta Q is equivalent to 0, and nozzle will not produce any amount of the work. So just to incorporate all these changes in the steady flow energy equation, it will become H1 plus C1 square by 2 is equivalent to H2 plus C2 square by 2. So from this you can find out what is the value of the C2. C2 is equivalent to square root of 2 into H1 minus H2, where H1 minus H2 is equivalent to delta H. So that is what is the exit velocity of the nozzle. So in the today's class we discussed about how can we derive the steady flow energy equation for the steam boiler, steam turbine and the steam nozzle. In the next class, once again, we will discuss about some more engineering applications of the steady flow energy equation. Thank you one and all for listening the interested topic on the steady flow energy equation.